boomerang comes back, let's consider some other possibilities. What are some other applications for a magnetic attraction? Here we have a magnetic construction set, which I've created a spinner with. And with the very powerful magnetic construction sets, you can make huge spinners, many times this size, about 8 times this size in weight, still being able to hold on. But what if I were to change this around? Right now I have, for example, south poles on the top of all of these magnets coming to this ball, and a north pole on the bottom of this magnet. So they attract each other by magnetic attraction. Opposites attract. But what if I were to change this around? This is going to fall apart on us when we do this. What if I were to change this around to where I had more repelling forces? I don't have any attraction. It won't hold up. So I can't build those cool spinners. We need to take advantage of magnetic attraction and magnetic repulsion, remembering that opposites attract and likes repel. So let's take advantage of magnetism a little bit more. Have a drink. This is a toy that I used to play with as a kid. Wonderful toy. I think they were called the wheelos when we were kids, and I think this is the magnetic wheel. I think so. I'll try to do this for a second, but if I try to go fast, it flies off. Lousy deal. Now what if some clever people came up with a new kind of magnet, a super powerful magnet called a rare earth magnet, an alloy of neodymium, iron, and boron. The rare earth magnets have a much stronger attractive force, allowing you to do things that the original wheelo could never, ever do. This toy works by the attraction of a magnet to iron, or a ferromagnetic material, and it continues to spin by conservation of angular momentum. Whenever something is spinning, it wants to keep spinning until some force brings it to a stop. It has a rotational, we say inertia. It has a desire to keep going. And if we take how heavy it is and multiply it by how fast it's spinning, that's called momentum. If something's moving straight, if we multiply how heavy it is, its mass, times how fast it's moving, that's linear momentum, momentum in a straight line. So we have a conservation of angular momentum here. Angular, rotating, changing angles. And so it wants to keep spinning, even if that means rolling uphill against gravity. These Wizmos are cool. A variation on that was a British toy called the Orbitoy from the 1950s. I've got one of those at home, but I didn't bring it. The Orbitron was based on that toy, and the Orbitron has, again, a dual track that the magnetic spindle holds onto. Again, taking advantage of our modern magnetic materials, we're able to have a spindle that will hold on even at very high speeds. So now, let's talk about energy. If I have something at the top of a hill, it is able to roll downhill and move faster and faster and faster. And as it rolls, the spinning of it means that it has a higher angular momentum. You've got more mass, the weight on the outside of this wheel, moving faster and faster, so we have a higher angular momentum. Now let's get this going really fast by letting it roll down this steep part of the slope. That allows us to make many revolutions. By the way, 11 or better is pretty good. I've gotten to 17, but I've been beaten by a 12-year-old at 19. So I'm going to have to go back to the drawing board on that. If I have it at the top of a hill, notice how it's not rolling very fast? It can pick up speed, but only at its steepest slope does it roll the fastest. At the bottom of a hill, it doesn't roll. And if we do have it rolling, but we let it try to go uphill, it slows down. Every time we make it go uphill, it slows down. So, in order to operate this toy, we want to let it roll downhill as fast as possible, manipulating this with our fingers, and let it pick up speed.